to our non-parametric statistics series. In our previous lecture, we studied McNemar's test, which compares paired categorical responses measured at two occasions. Today, we shall learn Cochran's Q test, which extends the same idea to 3 or 4 repeated measurements. If you understand McNemar's test, then learning Cochran's Q test will be much easier. This decision tree will help you select the correct statistical test. If the observations are independent, use chi-square test of independence. If the same individuals are measured twice, use McNemar's test. However, when the same individuals are measured 3 or 4 more times, Cochran's Q test is a correct choice. This is perhaps the easiest way to remember the purpose of Cochran's Q test. Imagine that a company conducts a compliance training program. Instead of measuring employee compliance only before and after training, the company measures compliance on 3 occasions: before training, 1 month later, and 3 months later. Because the same employees are evaluated repeatedly, Cochran's Q test is appropriate. Notice that each participant appears only once. Each row represents one employee. The columns represent repeated observations over time. The responses are binary, either yes or no, or 1 or 0. This is exactly the type of data required for Cochran's Q test. There are 4 important conditions. First, the outcome variable must be binary, 0 and 1. Second, the same participant must be measured repeatedly. Third, there must be at least 3 related measurements. Finally, the observations must be related because they come from the same individuals. This is the most important comparison in today's lecture. McNemar's test compares 2 related measurements. Cochran's Q test extends the same concept to 3 or more related measurements. If you remember this relationship, selecting the correct test becomes very easy. Hypothesis. Null hypothesis: the proportion of yes responses is equal across all measurements. Alternate hypothesis: at least one measurement differs. The null hypothesis states that the proportion of positive responses remains the same across all measurement occasions. The alternate hypothesis states that at least one occasion differs significantly from others. Unlike ANOVA, Cochran's Q test does not compare means. Instead, it examines whether the proportions of binary responses change significantly across repeated observations. Although Cochran's Q test has a mathematical formula, it is rarely calculated manually in research practice. Instead, researchers focus on understanding the logic of the test and then perform the analysis using statistical software such as SPSS or Python. Data entry is straightforward. Each row represents one participant, each column represents one observation occasion. Because the same participant appears on every occasion, the paired structure of the data is preserved. To perform Cochran's Q test in SPSS, go to Analyze, choose Non-Parametric Tests, then Legacy Dialogues, and finally Care-related Samples. Select all three repeated measurement variables and choose Cochran's Q. SPSS will produce the test statistics. Let us work on SPSS. I'm just going to show the file in Excel. I have 20 participants. Before the treatment, the recording has been done in yes or no. And after 1 month, again, their condition was seen. And in the third month, again. Now, this has been noted down in category yes or no. I can open the file directly in SPSS, open file, open data. You can open it, but let us try in a different way today. I'm just going to put the variables, copy here, and just putting it as transform. So my changed row has been changed, columns have been changed into rows, and I am putting it in variable view. So this is paste. So these are come the variables. First one is numerical 1, 2, 3. I'll put 0 decimals and only 2 width. The rest of the things are numerical, not numerical but string. So my yes is string, no is a string. So that is why I'm putting it as string. But later on we will change it now because string is not accepted by SPSS for any text, any analysis. So we have put a string here. And now I'll go to data view. And from here, from my Excel sheet, I will copy the data, copy it here. And I can open that directly in SPSS, but because the data is 20, only 20%. So that's why I'm just copying it in this one. Paste. So now this ID data is in the form of yes, no, yes, no. We will have to transform. Let us transform, recode into same variable. So what are the things we are going to before 1 month after this? Old and new values. Old value is yes. We will put the value as 1. Add. We are coding in the same this thing. No. And we are putting the value here as 0. Say add, continue, and OK. So this will be changed. We don't need the output. We will delete it. And now we have got 0, 1, 1, 1, 0. Okay. Now let us find out the Cochran's Q. Analyze non-parametric tests, legacy dialogues. In legacy dialogues, care-related samples. I repeat, non-parametric tests, legacy dialogues, care-related samples. I'll just click OK. It is not accepting. Why? Because 1010, they are still in string. We will have to go to variable views. We will change it into numeric, and we can make the change that width as 1, okay. And then we string again here numeric, and we will change it here numeric 1, okay. And then again numeric, and we will say okay, and we will say 1. Now all the numbers have been changed into numeric. Let us go to analyze non-parametric tests, legacy dialogues, care-related samples, and we will put this before, month, and after into our test variables. And we need Cochran's Q, not Friedman, not Friedman. And you want any statistics, then you can say descriptive statistics and all. So if you want, you can continue with this and say okay. Now in the output, you are getting a descriptive statistics. Before are 20, month 1 is 20, month 3 is 20. They are all related observations. Mean standard deviation is given, that is not required at all. Anyway, Cochran test frequencies are given before 0, 11, after 1 is 9 months, and all values have been given. 0 before 11 and 9, so 7 and 13, 6 and 14. And Cronbach's Q is 3.50, is treated as a success, and significance value is 0.174. It is more than 0.05. So we say we accept the null hypothesis. There is no difference between the three. Before month 1 and month 3 are same. There is no difference in the three. If the value comes below 0.05, we can say any one of them is different. Any one of them is different. SPSS output reports 3 important values: the Cochran's Q statistics, the degree of freedom, and the significance level. P-value determines whether the proportions differ significantly across the repeated measurements. Python performs Cochran's Q test using stats model package. The data are organized as columns representing repeated measurements. The function returns the Q statistics and the p-value. We first import pandas as PD, then we import Cochran's Q from stats model stats contingency tables. Our data is, we read the file, Excel file. Now I have saved this file in one of my folder. It is an Excel file. And the test data is data before months 1, months 3, which is in the square bracket. And then we say dot copy. And then we convert this data yes or no. As we converted the data in SPSS also, we convert it here. We say for columns in test data columns, test data columns is equal to test data columns dot map, in curly bracket, yes is to no 1 and no is to 0. See, the commands may look very, very tough for you, but when you practice it, use it, when you start using the Python, nothing is difficult. Results, Cochran's underscore Q test data, print Cochran's Q and real results statistics, and print p-value results p-value. Interpretation. I have already shown you the data in Excel sheet when we were working on SPSS. Now here I have started a new file, new notebook in Jupyter with my Python 3. Now the commands which are required have already been written. Import pandas as PD. Now this will do our some calculations. From stats model dot stats dot contingency table, import Cochran's Q. So this is the important function which is going to work. Funda will convert your yes, no into 1, 0, 1. So our data is, we are going to read the file. Which file is, I have kept this file in my D folder with my subfolder as T2C non-parametric, and video number 14 is there. This I have saved the file number SPSS Python. It's a long file, but you can use a small name and you can start it. Test data is data before month 1, month 3. Now this is in square bracket, dot copy. So from for columns, now this we have given the loop. I tried it in other ways also, but it was giving some warning. So that's why this we are starting the loop for column in test data, that columns, test data columns is equal to test data columns dot map yes is column 1 no column 0. So this will convert all our yes or no into 1 and 0. It will map it. Result will be Cochran's Q test data. So then we will print the results. Let us see how it works. We will run it. It will take some time because it is going to download pandas and then it is going to download the Cochran's Q. So the results are, we have not written here, we have found only the Cochrans, but we have not found written the p-value. So let us write down the p-value also. So I have written here print p-value result dot p-value. So we'll run it here again. So let us see the result. Now it is giving the p-value. Cochran Q is 3.5. P-value is 0.17377. It is up to so many decimals. You can reduce up to 3 decimals. The results are same as we got in SPSS. As the p-value is more than 0.05, we accept the null hypothesis. So there is no change. All the 3 columns are same before month 1 and month 3. Is straightforward. If the p-value is less than chosen significance level, we reject the null hypothesis. This means that proportion of positive responses is not the same across all measurement occasions. In our case, since the p-value is 0.174, it is greater than 0.05, we do not reject the null hypothesis. Therefore, there is no statistically significant difference in the proportion of yes responses across before month 1 and month 3. Common mistakes include using independent observations instead of repeated measurements, applying the test to variables with more than 2 categories, losing the pairing during data entry, and inconsistent coding of yes and no responses. Cochran's Q tells us that a difference exists somewhere among the repeated measurements, but it does not tell us where the difference occurs. Therefore, if the overall test is significant, the next step is to perform pairwise McNemar tests with an appropriate adjustments such as the Bonferroni corrections to identify the specific occasions that differ. This is similar to performing post hoc tests after ANOVA or Kruskal-Wallis. When reporting Cochran's Q test, clearly state the name of the test, the Q statistics, the degree of freedom, the p-value, and a brief interpretation in the context of your research question. Before choosing a statistical test, always identify the type of data and the study design. Number of variables and whether the observations are independent or repeated will guide you to the correct test. This simple decision tree can save researchers from selecting an inappropriate statistical procedure. Thank you for watching this lecture. I hope you now understand not only how to perform Cochran's Q test in SPSS and Python, but more importantly, when it should be used. In our next lecture, we will bring together all the non-parametric tests covered in this series and develop a practical decision tree for selecting the appropriate tests for different research situations. Thank you very much. Thanks a lot.
Always share the videos of Dr. Sachdeva to your friends who are interested in data analysis.